This is part of the series of online presentation materials for the WRF modeling system. This particular talk is on WRF computation, and it's going to focus on how to make the WRF model run effectively on a particular computer. Inside of the WRF model, if you look at both the data structures and the algorithms, you'll see that there is some inherent parallelism inside of the model. We take advantage of both OpenMP, referred to as shared memory parallelism, and MPI, referred to as distributed memory parallelism, inside of the code. Those parallel constructs for distributed memory require that we send information from one domain on one particular processor to another part of the domain on another processor. For effective use of that communication, we have some halo regions. Those halo regions and those communications end up constructing default domain decompositions. And those resultant domain decompositions, somewhat under the control of a user, can be fairly bad for performance or fairly okay for performance. There are some minimum and maximum boundaries, maximum based on the number of grid cells that one has, and minimum based on the amount of memory that one has. These decompositions are entirely a function of the total number of grid cells that one has, and that's for both the coarse grid and the fine grid. Finally, if you are interested in effectively running on a particular machine, the information to help you with the parallelism as well as any timing information are all contained inside of some runtime files that are generated during the simulation. For a suggested initial roadmap of the order to listen to the WRF presentations, an introduction to WRF, the fundamental capabilities of WPS, the description of general functions for the real program, running the WPS, and the setup and run for WRF should be taken initially by new users. There are a couple of presentations on fundamentals of atmospheric modeling and overview of parameterizations. Those should be taken together as a single lecture. Similarly, the physics part 1 and part 2 should be seen as a single lecture. The rest of the presentations can really be viewed in any order. This particular talk is WRF Computation. It's one of the 2 software engineering talks for WRF. The companion presentation is how to use the WRF registry. For most of this presentation, I'm going to be focusing on a benchmark that we set up for WRF version 4. Horizontally, it has 1500 by 1500 grid cells with 50 vertical levels. Even though it's 3-kilometer resolution, that doesn't really impact the timing results very much, other than how it would set up the domain, possibly with map factors and a resultant time step, and also the fact that we were able to exclude some particular physics. Because it's 3 kilometers, there's no cumulus scheme. For the default for version 4, both the moist theta option and hybrid vertical coordinate are activated. With a 3-kilometer domain, we should be able to comfortably use a 18-second time step. The entire simulation is only 6 minutes long, but that's because first we did a 10-hour spin up and then we did a restart. For the timing results that we're going to report, there's no I/O included. There is a radiation step and 18 non-radiation steps, and those are the numbers that are going to be reported. When we look at that domain, if we wanted to compute that entire simulation on a single processor, that would be choosing to do all of our work without parallelism. The idea is that one processor would work on the entire domain, one grid cell at a time. What parallelism means is that there are processes that are carried out simultaneously. So we can decompose the WRF domain horizontally, decompose the WRF domain into smaller pieces. And that allows us to distribute the work among multiple processors. Since each one of those subdomains is smaller, there is less work that is performed by each individual processor. That implies that the elapsed time that's required to complete the computational task for each one of the processors is reduced. So in the aggregate, the parallel job completes all of the work, but it completes it in less time. So if we initially start off with a single processor doing all of the computations for our domain, hypothetically, if we chopped our domain into 4 pieces, 4 equal pieces, and each piece had an individual processor, we should be able to get a speed up of nearly 4x. We use the word theoretically. If we went from 1 processor to 4 processors for a very large job, we would expect there to be some sort of speed up. But how effective is the WRF model at utilizing those additional processors? And this ability to handle additional processors, the measure of how well the WRF model is able to use those, gives us an idea of how well the WRF model is scaling. Traditionally on a supercomputer, the most efficient way to use additional processors tends to be with full or nearly full nodes. And for a very large job, if we have twice as many nodes, we would expect the time to be about half the original time. And if we had 3 times as many nodes, we would expect the model to be about 3 times faster, or a third of the original time. And then for n times as many nodes, we would expect it to be n times faster and 1/n the original time. And you can look at those progression of values and see that the scaling plots for using additional processors are going to look like hyperbolas. So this is a timing plot on the abscissa heading towards the right. The number of processors is increasing, and on the ordinate axis is the elapsed time to do the model steps. And as we move towards the right, the amount of time to do a model time step is reduced, which is expected as you use more processors. So this information is entirely accurate, but the presentation is just not all that easy to interpret. Traditionally, what people do is they recast this information into something that's easier to understand. So against a known 100% efficiency, or some sort of fixed quantity such as days of simulation per elapsed day of computation. In this plot, we see the same information, this idea of increasing the number of processors as you extend towards the right, but now the ordinate axis, the y-axis, is an effective number of processors used. So if we use 6,000 processors and our speed up is reflected as what would be perfectly efficient use of 6,000 processors, we would be on the green line. And typically, you would be underneath 100% efficiency. The base scaling for this is 2 nodes on Cheyenne. Cheyenne is the supercomputer at NCAR right now. I split out the radiation and non-radiation time steps. Specifically, radiation has substantially much more work, and because there's more work, even making the domain smaller, means that the parallelism is going to hang on quite a bit better. The non-radiation time steps have much less work, and as you start making the subdomains smaller and smaller, the time for communication starts to become dominant. Here's a list of timings for MPI ranks and radiation and non-radiation steps, and it's simply useful to see how the scaling works out. So we have a fixed size problem that we are interested in. It's the WRF model. We know the domain size that it's going to be. We know the physics options, the dynamics options that we're going to choose. We know how long the model is going to run. We know the number of vertical levels and the horizontal dimension size and the time step. The problem is fixed. What we want to do is look at how we can effectively utilize increasing numbers of processors on this fixed problem size. This whole area of endeavor of looking at increasing the number of processors on a fixed problem size is referred to as strong scaling. And it comes down to, if I have my fixed problem size, I would like the model to run in less time. And then how effectively am I using the machine, or are there considerations that I should have when I'm choosing these decompositions to help the model run as quickly as possible? Modern supercomputers have very large processor counts. The supercomputer at NCAR has over 140,000 processor cores, and that's distributed among over 4,000 nodes. When you have these very large processor counts, there are two kinds of parallelism that you traditionally take advantage of. Within shared memory parts of the machine, you are able to optionally utilize OpenMP. Between distributed memory portions of the machine, you are able to take advantage of MPI, message passing interfaces. Now, while a lot of this presentation is talking about supercomputers, it's important to realize that even laptops nowadays have anywhere between 4 and 8 processors. And that same idea of parallelism that works on supercomputers works on small laptops and desktop machines. First, let's start with OpenMP threading. OpenMP is also referred to as shared memory parallelism. It's also referred to as threading. The supercomputer at NCAR has 36 shared memory cores per node, and that means that we could have as many as 36 OpenMP processes running on a particular node. 36 is a lot more difficult to display than 4, so for these examples, I'm just going to show a maximum of 4 OpenMP threads. Shared memory processing and MPI processing differ in a number of ways. If we ask for 36 shared memory processes and only 35 are available, the model will happily run on the 35 available OpenMP threads and move on. For the WRF model, for small processor counts, and we're going to consider the number of cores per node to be a small processor count, shared memory parallelism is effective. For larger WRF jobs, the total number of OpenMP threads is typically not sufficient to run the model. So, for example, on our NCAR supercomputer, we were unable to run that 1500 by 1500 benchmark on a single node. So it couldn't run only with OpenMP. Usually what you see for very large jobs is distributed memory processing is required. People can take advantage of OpenMP and MPI together, but for large jobs, distributed memory is mandatory, and OpenMP memory is OpenMP processing is optional. To look only at the performance benefits of OpenMP, we have to modify the test case a little bit. So it's the same geophysical area, most of North America. And what we've done is we simply reduce the resolution by a factor of 10. So instead of 1500 by 1500 grid cells, it's now 150 by 150 grid cells. Instead of a 3-kilometer resolution, it's now 30-kilometer resolution. Because of the change in resolution, the cumulus scheme is now activated, and the time step is 10 times as large. Otherwise, everything else is the same. With this 150 by 150 benchmark case, this is suitable to try out on OpenMP only from 1 through 36 cores. With OpenMP, we have a couple of tile strategies that are available. We can specifically ask for an XY decomposition where the domain would be cut into something like a plus sign, or we can look at a tile strategy that is Y, which means we have long, narrow rectangles that have the full extent in the X direction and are very small in the Y direction. So small, thin rectangles stacked up on top of each other. This would be an example of what 4 OpenMP threads would look like if we were doing an XY strategy. This would be an example of what 4 OpenMP threads would look like if we were doing a Y-only tile strategy. We would expect the Y-only tile strategy to be a little bit better performance because the WRF model inner index for all of the computations runs in the I direction, and having a longer I direction value is going to give us a little bit more performance. That's reflected here in these two plots. On the left is the XY decomposition. On the right is the Y strategy for the OpenMP scaling. Typical of all the plots that we're going to show, as you move from left to right on the bottom of each plot, we are increasing the number of processors. And as you move from the top to the bottom, what we have is the effective number of processors that are being utilized. Again, perfect scaling would be along the green line. In both of these, you notice that the radiation steps tend to be much more efficient than the non-radiation steps. Now let's look at the other kind of parallelism, MPI parallelism. This is referred to as distributed memory parallelism. The idea here is that one processor can do work, but when it needs memory from another processor, it doesn't have access to that memory. So this is a distributed memory job. And to get access to data in another processor's memory, we need to send messages back and forth. This is the message passing interface. So with MPI, we can no longer assume that if we have next door neighbors, that the processors can access this same memory that they share. Even though on a single node, they do share the same amount of the exact same memory. For MPI, the processors are fairly independent in their own computational space. However, because this is a model that has horizontal differences, eventually we're going to have to send information to the next door neighbor. The domain is split into multiple pieces, and as opposed to shared memory processing, we can't just say that the section of the subdomain in the upper left-hand corner can grab hold of information in the upper right-hand corner along a neighboring boundary if it requires it. We have 4 separate processors, and each of these processors runs its own computations on its own subdomain, similar to OpenMP. But when it comes to the part where we have to do sharing of information from a next door neighbor, then the similarities break down. We no longer are able to assume that we have access to another processor's memory, and we have to send a message. When you run the WRF model, you'll end up with, if you have a 4-processor job, you would end up with processor 0, 1, 2, and 3. You'll notice that there are RSL, Runtime System Library, output and error files that are generated for processor 0, 1, 2, and 3. So in general, if you run N processors with MPI, you end up with 0 through N-1 for the RSL out and error files. If we compare MPI and OpenMP within just a single node, you'll see that the parallelism is similar, but the MPI is a little bit better. The work that has been spent inside the WRF model on MPI is reflected versus the results that you see with OpenMP. The 2 types of parallelism that we have inside of WRF are OpenMP, shared memory parallelism, and MPI, distributed memory parallelism. If we are inside of a single node, the parallelism for both of those is approximately the same. For a sufficiently large WRF domain, and 1500 grid cells by 1500 grid cells is going to be sufficiently large. 150 grid cells by 150 grid cells is not considered sufficiently large. So for a sufficiently large WRF domain, MPI can scale out to about 70% efficiency over a range of about 150 times a factor of nodes. The smallest node count that we're able to use is determined entirely by the memory requirements of the WRF model and the available memory on the machine. So if we try to use fewer and fewer nodes, the amount of total memory that's required to be fulfilled by individual nodes is increased. And we can get to a point where the WRF model requires more memory than the individual nodes would be able to supply. At the other end of the spectrum, the maximum number of MPI processes that we're able to do is based on how small we are allowed to make an individual subdomain on a processor. And that's a function of how wide the halo region is going to be when we start doing the model running. It's important to note that if you try to do scaling within a node, so within a single node, 1, 2, 3, 4 up through N shared memory processors, or 1, 2, 3, 4 up through N distributed memory processors, that scaling is not nearly as effective as, or even meaningful as, using full nodes on the supercomputer. Usually scaling is based on, this is how fast the model runs on a small number of nodes, and then we scale that up, increasing the number of full nodes that we're using. The differences between OpenMP and MPI, again, it's important to remember, OpenMP always requires a single node and shared memory. You can have OpenMP running within each of the nodes and then MPI across the nodes. That would work just fine. MPI, it was mentioned, gets its name from message passing interface. along the boundary of subdomains, we need to send information back and forth when we're doing our horizontal differencing. For performance purposes, there is a halo region that is set up to assist us with this message passing. We wouldn't want to send information to a neighboring grid cell every single time a piece of information is required if that information has not been updated. What exactly is a halo and when is it going to be used? Let's look at this assignment statement to P original I, K, J. For WRF, the only communications that we ever do are in the I and J direction. So K is in the middle of a 3D array, but it's really an IJ grid cell that we care about. So P original IJ is the average of PO IJ and PO I minus 1 J. If P original is going to end up on a momentum point, that means PO is on the mass point. It's in the middle of the two grid cells. The I minus 1 point is to the left of I, and if our original point that we're interested in, P or I comma J, is in the middle of the grid cell to the left is still contained in our set of grid points that are owned by our processor. Here, the 3x3 grid cells represent what our processor owns. So I minus 1, comma J and IJ are neighboring grid cells in the exact same processor. If we use the same equation, but now we move to the left one grid cell, we are now on the western boundary for IJ. What we need is I minus 1J, and it doesn't exist. What we could do is every time we do this computation along the I minus 1, or where we need I minus 1 along the western boundary, is we could do a communication, and depending on how many J rows there are, we would do a communication for each one. That's just not very efficient. Communications take much more time than local memory access. What we do is we say that we add an extra column onto our existing set of columns that we know about for our processor. This set of green columns is read-only. If we happen to need an I minus 1 value from our western boundary of a particular variable that is available, we can simply grab it from an available extra column that's tacked onto all of our arrays. So this halo region is updated only when that value on the right-hand side is updated itself. If PO, which is on the right-hand side, doesn't appear on the left-hand side, then if PO has previously been communicated and the halos have been filled up, as long as PO never appears on the left-hand side of the equal sign, the value for PO is not old and we can continue using it. Let's see how this concept of a halo works in practice. Here's our original domain, and we're going to chop it into 4 pieces. Again, 4 is a lot easier to see than 36 or even a couple thousand. Here are our 4 separate pieces. We're going to run 4 MPI processes from the lower left up to the bottom top. There would be 00, then 01, or 00, 01, 02, and 03 for the processor counts. If we look at the top right patch, it has halos to the left and below. The halos are not just a single column, but are larger than the biggest order horizontal advection operator that we're going to need. The lower right patch has halos to the left and above. The lower left patch has halos to the right and above. And the upper left patch has halos to the right and below. If we look at this upper left-hand patch, here are the halos attached to it, and this is information that's simply from the neighboring grid cells. If we overlay what a set of grid cells would look like, what we can do is say, all right, if I know what grid cells I have here, I can know whether or not I need to access the halo. So inside this particular MPI patch, this piece of the domain that a single MPI process is running, we have halos associated with this, but not every grid cell needs to access that halo. If we look in the upper left-hand corner of our domain, we see if we have a 4-point stencil, so we need a north-south point and an east-west point. A 4-point stencil in the upper left requires no halo access because we're far away from a boundary. Notice that the grid points that are along the eastern boundary and along the southern boundary each require a grid cell to be accessed from the halo. So the halo exists for every MPI process. The halo is only utilized when the stencil requires information that extends beyond the computational space for the individual MPI process. We've seen that running distributed memory processing with MPI requires that each of the individual processors have their own part of the domain that they work on. This domain decomposition, where we decompose the WRF domain into smaller pieces, allows us to take the total amount of work and divide it up among a number of processors. A user gets to determine how many processors to chop the domain up into, and that's a runtime decision. For example, you say MPI run-np in WRF.exe, where n is the number of MPI processes that you would like to have. So there are some questions. How do we determine how many processors we should use for a particular size WRF job? How do we know what that shape is going to be? And the how many and shape give us a third question. What are the performance consequences of those particular decisions? First of all, how many processors are we going to use? Well, there's 3 numbers that we really care about. What's the minimum number? What's the maximum number? And what's a good number to be using? The minimum number of processors that we can use for WRF is based entirely on memory. The WRF model has a fixed amount of memory that is required based on how many grid cells, how many vertical levels, what kind of physics, etc. If you choose a small number of MPI tasks, that means that you have a relatively large set of grid cells in a particular patch that an MPI process is running. If that amount of grid cells has an aggregate memory requirement larger than is available on the particular node that you're running your MPI process on, the job will fail. So the minimum number of processors is based on matching the memory that the WRF model needs with that minimum value available on the MPI process that comes from the node. In the case that we were running, the 1500 by 1500 benchmark, we needed a minimum of 4 nodes for the standard nodes and 2 nodes required for the large memory nodes. We could not get WRF to run on a single node. It just required too much memory. The maximum number of processors is based on the underlying assumptions and algorithms that go on inside of the communications for WRF. We can't make the model use domains that are smaller than 10 grid cells on a side, and so it's a rectangle. So if you have something that's 12 by 12 as a decomposed domain, that would be okay. But 8 by 15, for example, would not be okay because one of the resultant sides is less than 10 grid cells. For the 1500 by 1500 benchmark, the maximum number of processors we could run would be 150 units of processors in one direction, 150 units of processors in the other direction. That would be 22,500 MPI processes would be the absolute maximum that you could run for this domain. The timing performance would be not very good. That's the amount of work inside of a domain that's only 10 grid cells by 10 grid cells is fairly small. The amount of time to do a communication with next door neighbors can be considered fixed. So as the amount of work is reduced in the processor, the fixed amount of time that is required to do a communication starts to become dominant. The recommended number of processors is going to be some arm waving. It's going to be based on decisions that an individual user has to make. Is it more efficient to utilize the machine well, having a large number of jobs using a reasonable number of processors, or are there time constraints that mean that I need to get this particular job done very quickly? As long as there are enough processors and not too many processors, then the WRF solution is considered correct. There may be bit-for-bit differences, but you can get identical solutions if you turn off optimization that do not depend on the processor counts. The recommended number of processors is going to be a user-determined value that takes into account the amount of time that is allocated to run a job and the rest of the community that is on the particular machine. So now that we know that how many processors we can be interested in with a little bit of arm waving, the way that those processor decompositions are generated is important. By default, when you ask for n processors, the 2 closest multiplicative factors for n are chosen as the decomposition. So for example, for 32 processors, it's a 4 by 8 decomposition. It's not 1 by 16 or 1 by 32 or 2 by 16. For 144 processors, It's 12 by 12. It's not 4 times 36. It's not 9 times 16. The larger of the two default factors decomposes the j direction. Because we want the I direction to be as large as possible, we use the smallest factor to decompose in the I direction. It's important to avoid prime numbers or large or composite numbers that have large prime factors. For example, 61 is a prime number. 122 is a composite number that has a large prime factor. Here is an example domain, and we have asked to decompose this domain into 70 MPI tasks. On our MPI run command, we said something like MPI-NP70 and WRF.exe. When we have 70 tasks that are requested, first the model finds the two closest factors to 70. That would be 10 and 70. It's not 14 and 5. It takes the larger of those two, 10, and that's what it uses to decompose the number of tasks in the j direction. It takes the smaller of those two, 7, and it uses that to decompose the number of tasks in the I direction. This is how we get 70 total tasks. This is a reasonable decomposition for a domain. Notice the very different way that 70 tasks is decomposed compared to 71. 71 is a prime number. When we try to get the two closest multiplicative factors, we end up with 71 and 1. That means that we decompose the north-south direction into 71 pieces, and the I direction just is all the way from the left to the right of the original domain. Because of the requirements that we've previously talked about, where we need at least 10 grid cells in each direction, the minimum j dimension for this domain would be 710. This is a particularly poor choice for a decomposition. An additional thing to keep in mind when doing domain decomposition is the impact of your choices on nesting. Within the WRF model, all of the domains, regardless of the number of grid cells on the domain, use the exact same processor counts in the I and the j directions. While the sizes of the decomposed domains are not the same, the exact same processor decomposition is used. So if there are 10 decompositions in the j direction and 7 decompositions in the I direction for domain number 1, that exact same number of I and j decompositions is on each of the nests that are inside of the WRF model. If you choose coarse grid domains and fine grid domains that have a big difference in the number of grid cells, this will negatively impact your timing performance. A number of users incorrectly choose to have a relatively small coarse grid and have a relatively large fine grid. The relatively small coarse grid restricts the total number of processors that are available because you can only have a number of processors that will get you down to a particular minimum domain size, 10 grid cells by 10 grid cells. A larger coarse grid allows you to have more processors, which allows you to run more processors on the fine grid. The fine grid is always the expensive grid in the WRF model. Here's an example domain with an example very small decomposition. Domain number 1 has the X and Y dimensions as 74 by 61, and the fine grid is 112 by 97. If we look at a default decomposition on domain number 1, the largest number of processors that we would be able to have would be 36 processors, because the J direction is 61. The largest number of decompositions we would be able to run in the J direction would be 6. And by default, the J direction is the larger of the two. So the largest number of processors we would be able to run would be 6 by 6. It's 36 processors. On the nested domain, the largest number of decompositions that we would have, again, is a function of J, and that would be 9 in the J direction. We would be able to run 81 MPI processes on the nested domain, so more than a factor of 2. Even if we use namelist options, the coarse grid being much smaller than the fine grid restricts the total number of MPI processes that we are able to run. The number of MPI processes makes a substantial difference in the timing performance of the resultant elapsed time that you're going to run for the simulation. To see how efficiently the WRF model is running, to see how effectively the WRF model is using the computer that it's running on, we need to have some information, timing information. That information is provided with a couple of text files that are generated for each of the MPI tasks. When you build the WRF model in distributed memory and you run it with MPI run-np-in, what you end up with are a pair of text files for each MPI process. rsl.out.nnn, where NNN goes from 0000 up through n-1, and rsl.error.nnn. The output and the error, for the most part, have the exact same information. Sometimes if there is a segmentation fault, only one of these will have additional information. So usually what I do is just look for the larger of the two when I'm debugging. But for timing performance, the RSL out, the RSL error have essentially the same information. And there's a lot of good timing information and domain size information inside. Inside the RSL file, there is information, two kinds of information that will allow you to figure out some basic speed information for WRF. So even with a traditional idea of speed, where you have some idea of a distance and some idea of a time, we can consider the total number of grid cells that we are processing as a numerator and the elapsed time as some sort of denominator to give us this idea of how fast things are going. To know how big our domain is, right up towards the top in the RSL file, we are told how many MPI tasks are used. In this case, it was 108. And by default, as was stated before, the two closest factors for 108 are 9 and 12. The larger of those two decomposes the j direction. The smaller of those two decomposes the I direction. So the statement up at the top says in tasks X is equal to 9, in tasks Y is equal to 12, telling us the decomposition and the total number of processors used. The next set of information in the RSL file is about the resultant domain sizes from that decomposition. You'll see the middle letter is D for IDS, IDE, JDS, JDE. That D is domain, the entire domain size. IDS, IDE is domain start, domain end. In the I direction and J direction, this is 1500 by 1500. So it's 1 to 1500 and 1 to 1500. The M in the middle of the next line is memory size. This is the size of the array that the MPI process has, and this includes a surrounding halo region on both sides. The IMS, IME, JMS, JME, these are variables that are defined inside of the WRF registry. The total size that is used for computation is the next line down. The letter P is in the middle. The mnemonic there is for patch. This is the size of the domain over which the MPI process does all of the computation. So for decomposing a domain 1500 by 1500 into 108 pieces, our resultant domain size, our patch size, is going to be 167 by 125. For that particular domain size, 167 by 125, including some halo stuff, the total allocated space, and this is heap memory, so this is not something that is adjusted based on going in and out of a subroutine where the stack is, we add to the stack and then the stack frame is thrown away. The heap memory is allocated at the beginning based on some runtime choices. The user is able to take this information and get an idea of how much space the WRF model is actually using. And if you know what the available amount of memory is on your machine, you can adjust the WRF domain size, number of vertical levels, physics options, etc., so that you can get exactly how much would fit on that particular process. Also, for performance purposes, timing is usually a big deal. There are a couple of lines that are output inside of the RSL file that are important. Every single time step has the amount of time that it takes to run that time step. If you run a nested domain, only look at domain 1, because domain 1 has the aggregate of all of the other domains inside of it. In this particular case, the first line shows us if I'm outputting some data, how many elapsed seconds did it take to output this data file. The second set of lines show us how much time did it take to do some computation. Usually the first line is including the I/O and some pre-processing that goes on. So looking at this data, we would say about 7 seconds to run a single time step of the model and about 140 seconds to output some data. If it takes a factor of 20 to output data compared to a time step, it's probably an indicator that we want to spend a little bit of time and do some optimization for I/O. This presentation on WRF computation obviously has centered on the one thing that is important for all numerical weather prediction models, and that is parallelism. To actually utilize parallelism inside of the WRF model is fairly simple. The code has to be built either for distributed memory or shared memory, or it can be built with both. How effectively the WRF model is able to use these additional processors is referred to as scaling. There are two different kinds of parallelism that are supported inside the WRF model, and they can be used separately or together. For small domains, OpenMP or MPI could be used individually inside of a single node. Once a domain is fairly large and you need more than a single node, OpenMP could still be used within a node, but MPI is required to go between the nodes for communications. The communications are a real performance bottleneck, and an engineering solution to that is to use what is called a halo region inside WRF parlance. This is an additional set of rows and columns that are attached to each of the arrays, and they are read-only memory. The whole purpose for this is to allow the WRF models to continue to do finite differencing and to not have to do a communication every single time a value is needed that's just outside of the computational domain. Because we do these communications, because there is parallelization for distributed memory, the resultant domain decomposition becomes something that is important. The domain decomposition is, by default, handled as choosing the two closest factors for the total number of processors that are selected. The larger of those two decomposes the J direction. The smaller of those two decomposes the I direction. A reasonable number of processors is somewhere between a maximum and a minimum. The minimum number is a function of the amount of memory that the WRF model needs and the amount of memory that the node is able to provide. The maximum number of MPI processes that we are able to use is based on how many grid cells are actually in the domain, because we are allowed to get down to a domain that has a resultant size that has an I direction and a J dimension that are no less than 10. These dimensions and decompositions then are intrinsically hooked up together, and that's true for all of the domains. The number of grid cells in the coarse grid and the fine grid may be different, but the resultant domain decomposition, how many MPI processes in the J direction, how many tasks in the I direction, is the same for each one of the domains. To actually do some performance studies, it's usually necessary to gather some information from inside of the RSL files. The RSL files contain information that say exactly how big each individual process is and how much time it took for each of the time steps to be completed. If there are any questions about this presentation or any of the other presentations in the rest of the WRF modeling system tutorial, please go ahead and send those to the WRF forum. There's a general statement for the WRF user support that is provided, and there are a number of resources that a user can take advantage of. WRF has a nice homepage that details not only information and documentation, but also schedules and availability of tutorials and workshops. Finally, the WRF and WPS source codes are maintained with an open development capability on GitHub at the following locations.